Before I go into cascading, one more issue came up, and that is that there are several things that the kind of traffic, like particularly there was some problem with promiscuous traffic. So there are some machines which want to see all the traffic. Okay, and when you do these kind of switches, then there was a kind of problem. So they had to come up with a new concept called channels. So let me explain how that concept comes in. So this is your machine. In this machine, you have two switches, VEB, and I have used the word eSwitch here. Now let's see what is eSwitch. eSwitch is actually in the hardware. So the NIC implements a switch. The NIC implements a switch. So this is not software switch, this is eSwitch. Okay? And this is in the software. This is called vSwitch. So now we have P, V, and E. Everybody knows P and B, now know your E. E is electronic. So now you have these two switches, and this was done by, and I could have changed the word E here, because depending on what NIC you have, it might be able to implement VEPA or VEB. So I just showed you some examples. And there are some machines which do not go through the switch, they go directly. And there is only one physical NIC here. You see solid line here. This is the boundary. And now this is a physical NIC, a physical switch, external switch. So basically what it is that and these are called VSI. These interfaces at the switches are called VSI. So VSI is the virtual system interface, virtual station interface. So this is red and this is blue, this is red. Those are the colors of the VLANs. So this blue can talk to this blue, these reds can talk to each other, but the blue cannot talk to red, right? That is the VLAN. Now all of this traffic goes through, and these switches also have some ports coming out which somehow get combined and get into a single queue and then get out. Alright, now we need to know here, if we are going to do all the work here, then we need to know which switch and which port these things came out. Right? And so basically we need to divide this NIC into channels. This is one physical NIC, a physical link, but we need to divide that into channels we call S channel. S channel is the traffic coming from multiple ports. So there are 3 ports here. We see 1, 2, and 3. These 3 traffics have to be distinguished to be set up 3 what we call S channels. So these are virtual channels actually. So this switch now implements 3 virtual ports, and these things are somehow connected. Alright? What that means is that we put VLAN inside a VLAN. So this is Q in Q. Basically, there is a VLAN between these 2 ports, and so basically when the traffic comes out here, we look at this outer VLAN and we decide that this is going to this port or that port or that port. So that's how we can share this. If we didn't have that VLAN stuff, then all of this traffic will come and there is no markup left by anybody here as to which switch and where it came from, and we would be confused because switches don't put their addresses on anything. So S channel. S channel is basically these virtual channels which is partitioning this link or this little link here, and they are service channels, and they are basically another layer of VLAN. So this traffic is already all VLAN, and then we put another VLAN on the top of it, Q and Q. Yeah.
Do you have any specific limit to use the Q and Q rather than the legacy VLANs?
Oh. So basically when you need 2 VLANs here, right? Legacy VLAN is there already. But now you need to distinguish. You see, this is also blue and this is also blue. But we need to distinguish which switch it came from. So, I mean, basically, so you need, this is basically we go back to the same thing like we talked about why the providers need their own VLANs, because they don't want to deal with the customer VLAN. So these are customer VLANs. This is the provider VLAN. We learned it in carrier concept, so we kind of have a big idea that carrier networks are big, but here there is a tiny carrier network, few centimeters long. Yeah.
So, what's the difference between connecting VM to through the channel to the switch, and between connecting the VMs through the VEPA?
So this one directly, right?
Yeah.
Okay. Basically, this will be a little bit more work on the part of the VM. So this VM actually has to implement VNIC. I mean, we has to implement more than these other VMs. Okay. So generally there is some switching part, etc., which these will provide, whatever service these guys are providing. So this VM will have to do a little bit more work. And so I have shown you all the three possibilities here. You could just use only one of them. For example, you could just have one vSwitch which covers all of the ports, or you could have things like that I showed you, right? So this is just I have showed you, try to show all three possibilities: directly connected, connected to a VEPA, connected to a VB. Okay, so let's just remember. So we know what is the VSI. VSI is this set of ports. Embedded eSwitch. eSwitch is something that is in the NIC hardware that can implement web or VEPA. And then V port is the VEB port, the virtual egress ports. These are the egress ports of the switches, right? Egress port on a switch are ports on vSwitch with directly, okay? Or if they are directly connected, then there is also a V port. And the S channels are these logical things which have been set up. You see, the problem is that when you have these virtual machines and they have the NICs, some of them be part of some multicast traffic, right? So you cannot just look at one destination address and say it goes to this VM. The second problem is that some of these machines might be what we call promiscuous. What does promiscuous means? Yeah. Promiscuous means they listen to all the traffic. Alright? They are just, you can put on the Ethernet, and actually on the switch it is generally not possible, because on the switch you can just listen to all the traffic that is coming to your port. But if you have a switch which allows management, you could set a port to be promiscuous. Okay, so all the port traffic will go to that port, right? And so those things have to happen in this virtual environment as well. And for that reason we need these channels. So these channels are between the exit of the switches here, and we have a corresponding thing here, the entrance for them. So these exits of the switches are called V ports. The entries are called what? These are called VSI. Those are those are virtual station interfaces. And these are the switch interfaces, virtual switch interfaces, including this one which is directly connected is a virtual switch interface. So basically these three have a corresponding image here, and so we need to decide here what goes where, and we send it on that channel. Okay? So and so that way not everything goes to everybody. Okay, that is why you need these S channels. S channels are the second layer of VLANs which limit the traffic to particular switch ports. Okay. Now here's an example. This VM wants to talk to that VM. Both of them are on the blue VLAN, so they could talk. Okay. So it sends a packet to first VEPA switch, and that says, okay, all right, it's going to go outside. And then here, this component, which we SVLAN component, this is the component that actually is encapsulating. This is the one that creates a new VLAN. So here, a new VLAN is put. So now the packet is encapsulated. Number 2, packet is encapsulated and a new VLAN is added. Now it gets out here, and based upon that VLAN, basically it gets to this component, puts it into this port 3, where that tag is taken off. Now it is only one tag left. In this part there are two tags. Okay, I didn't have a way of showing this thicker line, but basically to show that this is two tags, this is one tag here. Now one tag is left, it could go out or it could go inside or whatever, it doesn't matter, in this blue VLAN, and then finally it ends up here on this port where it has to go there to E port because they figured out that the destination is here. So they have to put a new tag here again. A new tag is put and the packet goes in, and this component here, this other component, decide that it has to go to that port, and it goes finally out to VM. Now, I should have ideally shown much of this into dotted line, but I forgot. So basically, see, thing is, the idea is that basically things are correctly labeled, but sometimes the dotted and the solids are didn't get time to put them in the correct lines. But the idea is clear. There is single VLAN here, second VLAN is put here, and then second VLAN is taken off here, second VLAN is put here, and then second VLAN is taken off there. Alright? So this is the S channel. There is an S channel between A and A, there is an S channel between B and B, there is an S channel between C and C, D and D, and E and E. So there are 1, 2, 3, 4, 5 S channels. Okay, here's the thing. No, let me just say this one. I have shown you an example where it is necessary. Suppose this is a VEB switch, and this VM talks to that VM. This switch will reject it right away because this is you are a yellow and this is a blue. Right? And that's all. But suppose by chance these both are yellow. Then VEB switch will not forward it outside. VEB switch will just short circuit it. Right? So there are other possibilities which I have not shown here. But this particular traffic which is going from here to there really has to get out because first of all it is VEPA. Right? Second of all, it is connected to a different switch. VEB, it still has to get out because the thing is, it cannot just forward here. So it has to give to somebody else to get there. They are not connected by the same web VEB. They are not connected to the same switch. Yellow is the customer VLAN.
I mean the yellow on the right.
Yellow on the right.
Yeah.
This yellow?
Yeah.
Oh, that is just... Okay, and that's actually... random. I should have put a random color here, or I should have put this dark gray here. Yeah, should not be yellow.
Yeah.
No, actually there are many purposes. First of all, this belongs to, let's say, company X, and this belongs to company Y, this belongs to company Z. There are many tenants here, and so you cannot just put all of them on one switch and let them talk to each other. All right, and this company may not trust this switch because they don't want them to see their traffic. So they want to. This is multi-tenancy, remember. The companies don't trust, they're all on the same physical machine, same physical hardware, but they cannot use the same, even virtual switch. So the thing is, who will own that switch? The thing is, if there is just take any two companies which are enemy to each other, okay, Samsung and Apple, right? So this belongs to Samsung, this belongs to Apple. Would they let it go to the same switch? Maybe not, until they encrypted it. So the idea is that these switches, virtual switches, will have to belong to somebody, so they will have their own switches. So they will not just have one switch until the thing has been encrypted, things like that. So there is a lot of complication here. So there is some reason for people to have more than one switch inside. Yes, you could have. You could have just one big switch, and then everybody is connected, and then traffic remains inside. That's why IEEE has standardized both methods. The same standard covers both VEB and VEPA. Okay? And then we had this example where we saw that if the traffic is coming from this switch port, it goes to that here. That way all the traffic that is coming from here goes there and not to these other ports.
So for this example, when the traffic is in the external switch, how does it know which port should it forward it to? How does it
on this side.
On the right side.
On this side?
Yeah.
Oh, that is basically, we'll take off the VLAN and look at the MAC address and the VLAN of the inner thing, right? Okay. And then it will decide whether it goes out to the world or whether it goes back to the same host. So this is purely the standard standard VLAN MAC address forwarding.
So is it known that, for example, port E is responsible for VLAN's number?
Yeah, so this is known. Basically, everybody knows the VLAN membership. They learn it by, basically source learning. And so this knows that there is a port here which is blue and its MAC address is such and such, and actually in the VLAN blue. So that address, so based upon that address, it comes here. And then it is encapsulated again in another VLAN, so it doesn't go anywhere else. It goes straight to this E, and then it goes out. So now the next thing is, how do we manage all these NICs? And this is very important today, because nowadays we have thousands of these things. I mean, if you have thousands servers, you have 10,000s of VMs. Right? Sometimes in millions of these things. So you cannot just go and program each one individually. There is no manual work at all in the data center anymore left. If there is a manual work, it is what we call orchestration. Everybody knows what is orchestration? What it means? Everybody knows what is an orchestra? You know what is an orchestra? You go to a place where you listen to music and then that is an orchestra. Okay, so there is a director there who moves his hand like this, and everybody changes their tune, and they moves it like this, and then like that, and everybody changes the tune. That is orchestration. With one hand, you could move 1,000 people. Right? So with one command, you should be able to program 1,000 VMs. And so orchestration is done in the networking, and the way it is done is that there are standard profiles. So there are standard profiles which are, so we say, okay, this is profile type X, Y, Z, just whatever name you want to. There's no IEEE standard, it's just, the provider standard. Okay? So they just keep them stored in the disk someplace, and they say, okay, I need 10 of these, I need 20 of these, I need 5 here and 2 there and this and that, right? So those profiles, those are called network port profiles, they are applied to the VM. And a OVF package, now you know what is OVF. What is OVF?
File system.
Yeah, virtual file system. So that OVF, overlay virtual file system, or something like that, package is may or may not contain. So thing is, VM is created from OVFs. First of all, for each VM there is a disk that you just attach, give it to the server and say, okay, here it is. Start a Linux, start a VM, Windows 7, here, right? So those OVF files may not have the network profile in it. Because when the OVF were written, they didn't know what kind of network I will have. And after VM instantiation, generally the networking team applies a port profile to the VM. And now there are two different teams here again. There is a server team which knows all about the applications, and there is a networking team which knows all about networking. So the server team starts the VM, and the networking team starts the network or that VM. So DTMF. So DTMF is data something management forum. Data task management forum. Actually, this is wrong. DMTF, I think it is. And DMTF will be Data Management Task Force. So if you go to the abbreviation list, it might be correct there in your handout. DMTF has extended OVF format, and they are the one who actually started the OVF format to begin with. They support the port profiles now, and that port profile includes resource allocation profile, resource capability profile, and vSwitch profile, etc., etc. You might say, well, I need a 10 gigabit Ethernet port on this, and that 10 gigabit Ethernet port should be on the blue VLAN, and that blue VLAN, whatever else you need to tell, about that switch, you just put that in that profile. And this is how you get 10,000 blue VLANs, blue VLAN nodes, because you just give them all the same profile and they have the same color and everything else, and suddenly you have a VLAN all over the data center. Okay, so that is about the management part of these machines. Edge Virtual Bridge, was VEB? Could be VEB. Virtual Edge Bridge. I'm actually, this is wrong. Basically, you can correct it to VEB management. But the thing is, this applies to VEPA as well. So it is not really specific to VEB. It is basically virtual bridge management. So maybe I should just remove the word E there. So,
EVB is used generally for both VEPA and VEP. So this is right. EVB.
It includes VEPA as well?
VEPA and VEB. VEB is the technology, VEPA is the technology, and EVB is the...
Oh, I see. Edge virtual bridging.
Yeah.
All right. That makes sense. Okay, let me explain what is said. That the standard is 802.1 QBG. Right? So either I could say 802.1 QBG management, which includes two different kinds of bridges, and it also called Edge Virtual Bridging. The name of the standard is Edge Virtual Bridging, EVB. Okay? So it makes sense now. EVB includes two things, BEB and VEPA. And also includes S-channel, by the way. S-channel is also in the same standard. And by the way, all these standards are available for free. For those of us who need them, we always keep them. I have all of these standards in my computer right here. And we read them, when needed. And when we need the authentic information, we read them. So you should get used to reading the standards. Then there is auto discovery. There are lots of protocols for management, just like for OAM. For the carriers, they made OAM. For the data centers, they have protocols that allow the management. And we will not go into the detail except listing the names here so that you know that there are. So there is Edge Discovery and Configuration Protocol, EDCP. There is a VSI Discovery and Configuration Protocol. There is S-channel Discovery and Configuration Protocol. Edge Control Protocol to provide reliable delivery for VDP. Now VDP is the VSI Discovery. So let me just say a little but one sentence more about each of these. VSI Discovery. Basically we need to know how many ports are here on this side. Those are the VSIs. And so basically there is a protocol which says, okay, how many ports are there? Some switch asks some other switches that broadcast a request, and then somebody says, okay, I have 1, I have 2, I have 3, I have 4, I have 1, and then it adds up. That's the discovery. So there is a VSI discovery and configuration. Then it says, okay, all right, what, either they will themselves know that I am in the blue LAN, or they will say, okay, you are on the blue LAN now. Things like that, okay? Similarly, then there is a S-channel discovery, and there is a Edge discovery and configuration protocol. So the Edge would most likely, and I cannot be sure, is vPort discovery. We need to know how many vPorts are there so we can set up the S-channel, things like that. So all of these discovery protocols are included there. And then, since this thing has to be very reliable and they don't want to use TCP, so they have their own transport protocol, which they don't call it transport, they call it ECP. They don't call it TCP, they call it ECP. But it has all the same features as TCP, which means it has windows, it has, flow control, congestion control, three-way handshake, everything. But they don't want to. Can you understand why they don't want to use TCP? Because they are IEEE. And TCP is IETF. So, so you cannot design layer 2 which depends upon somebody else. You want to have complete control over your layer. If suppose somebody doesn't have IP and they have Ethernet, what do? Right? So it's not political, it's just self-sufficiency in the sense that Ethernet is designed for all layer 3 protocols, for all layer 4 protocols. We cannot just depend upon one layer 4 protocol for anything, including the management. So they designed a reliable protocol for that.